Hello, everyone. My name is Mandolanik Kumar, and I am from Colorado State University. I'm going to present our research work on cross-temperature reliability concerns of 3D NAND flash memory chips. In this presentation, I'll go into details of cell-to-cell variability analysis of those memory cells, and I'll present two possible countermeasure techniques. Here's the outline of the presentation. First, I'll talk a little bit about the conceptual background of this cross-temperature reliability issue and describe the motivation behind our research. Then I will present the experimental results measured from commercial off-the-shelf memory chips, 3D NAND chips. After that, I'll explain the root cause behind this cross-temperature reliability phenomenon. I'll present two possible countermeasure techniques, and then comes the summary and conclusion. As you all know, NAND flash memory technology is the most mature memory technology nowadays due to its three-dimensional integration, very high chip density, and low power operation. It has become the primary workhorse of permanent data storage nowadays. But if we program the NAND flash memory chip at one temperature and try to read it at a different temperature, we observe a large number of error bits. So to explain how that happens, we present the conceptual diagram on the right. Here, the red distribution is a page cell distribution, the threshold voltage distribution of the cells of a memory page. When you program it at a temperature, let's say high temperature, and if we try to read it at a different temperature, let's say at a lower temperature, we get this black distribution. And it is noticeable that the black distribution have shifted, and also it is significantly wider. Now, how that happens is we think there are three groups of cells, namely red cells, blue cells, and green cells. And the red cells have very high temperature coefficient, and the blue cells have very low temperature coefficient, and the green cells are those which have average temperature coefficient. The value of temperature coefficient indicates how the cells will respond to sensing temperature change. So when the sensing temperature changes, the threshold voltage sensed values are different than the one that were actually programmed. So the cells with high temperature coefficient will undergo a very large threshold voltage shift because of this temperature change. And the cells, like these blue cells, they will undergo a very small amount of threshold voltage shift. And of course, the green cells will show average behavior. Now, because of this variable VT shift, depending on their temperature sensitivity, of course, the distribution will shift to right or left, depending on the temperature change direction. And the distribution will also get significantly wider because not all cells behave in the same way due to this temperature change. Here's our experimental setup. We use commercial off-the-shelf memory chips, and we use a hardware board, which is in-house built, and we interface these chips through this hardware board, and we can send commands to program erase and read memory blocks or pages from our computer. On the left side, we show the page distribution that of highest state of a memory page, the VT distribution of a memory page. This is the first phase of our experiment, where we programmed the memory chip at a low temperature and read it at the same low temperature and a different high temperature. By low temperature in our experiment, we mean minus 15 degrees Celsius, and by high temperature, we mean 45 degrees Celsius. So from the figure on the left, we see that this red distribution is the distribution which we get when you read the chip or the block at a different temperature, which is high temperature here. This distribution, red distribution, is wider, the way we explained in the previous slide. On the right, we show the same distribution of the same state when the experiment was reversed. We programmed the chip at a high temperature and read it at the same high temperature and a different low temperature. Now the different temperature distribution, the black one, that is wider here. So in both direction of temperature change, the threshold voltage values have shifted, and the threshold voltage distribution has become wider. We don't see the shift of the distribution here because the commercial chips have on a chip temperature sensor, which actually adds and takes care of the mean value of the distribution, but it cannot take care of the widening of the distribution. So still there will be a lot of error bits observed when the cell is sensed at a different temperature. Now, according to our hypothesis, there are cells that have high temperature response, and there are cells that have low temperature response, which are high temperature coefficient or low temperature coefficient cells. So to explain that, we present these two scatter plots. On the left is the scatter plot of threshold voltage shift values of the cells from the first experiment. And in the middle, this scatter plot refers to threshold voltage shift values of the cells, of the same cells from the second experiment. In the first experiment, we program the chips or the cells at lower temperature and read it at high temperature. And then we subtract the high temperature threshold voltage from the low temperature threshold voltage to get the DVT values. And on this second scatter plot, we reverse the experiment. We program the chip at high temperature and read the chip at low temperature, and we calculate the threshold voltage values in the same way. Now, we see that always in both cases, there will be some cells that have very high threshold voltage shifts. By high, I mean significant amount of threshold voltage shifts, around 0.2 or 0.1, indicated by this red circle. And there are cells indicated by these blue circles that have very small amount of threshold voltage shift, indicated by negative values like minus 0.1 or minus 0.2. So these blue circle enclosed cells are the low temperature coefficient cells, and these red circle enclosed cells are the high temperature coefficient cells. Now, to make sure that this is this placement of these cells of high temperature coefficient or low temperature coefficient, to make sure that they are not random, we construct this correlation plot on the far right. On the x-axis, the threshold voltage values of the cells when the experiment was done in the first phase, that is program at low temperature and read at high temperature. And on the y-axis is the threshold voltage shift values when the experiment was reversed, that is the chip was programmed at high temperature and read at low temperature. Now, this correlation plot clearly shows us that there's a group of cells that always responds strongly to temperature change, let it be low temperature to high temperature or high temperature to low temperature. And there are a group of cells enclosed by this blue circle that responds very weakly, always when the sensing temperature is changed in whatever direction. So this correlation plot shows us that being the high temperature coefficient or low temperature coefficient of those cells are their physical property. There is something physical with those cells that makes them respond in these two different ways. So to explain the nature of those cells being high temperature coefficient or low temperature coefficient, I present the root cause analysis because this polysilicon channel of this 3D NAND memory structure is very granular. Now, this random profile of grain boundaries and this grain boundary traps in the polysilicon channel actually affects the current flowing through the polysilicon. Now, when a memory cell is programmed, the incremental step pulse programming scheme, that is ISPP, it makes sure that a tight DVT distribution is achieved. And the way it is done is, if we look at this figure, when a chip is programmed or a memory page is programmed, the cells which have different IV characteristic, the sensing current is, ISPP makes sure that the sensing current is at the narrowest crossing point of those IV characteristics, so that a tight VT distribution is observed. But when the sensing temperature changes, like when it is read at a lower temperature, or when it is programmed at a lower temperature but read at a high temperature, this IV characteristic slope changes because of this temperature change. And why that happens is this random profile of grain boundaries in the channel, they affect the M factor, the subthreshold swing factor of the subthreshold current equation. And this M factor determines the temperature coefficient of a memory cell. So depending on this very high value or small value of this M factor, the subthreshold slopes change when the sensing temperature is changed. So when sensing temperature is changed, because this isense level is fixed of a chip, so when it is read again, now the VT distribution gets an extra spread, because the crossing point of IV have now moved up or down depending on the temperature change direction. So this is how the polysilicon grain boundary properties and percolative current conduction properties affect the IV characteristics of threshold swing, and the subthreshold swing factor actually determines how spread out this threshold voltage distribution would be. So to counterattack this phenomenon, we present here two different scheme. On the left is the temperature dependent sensing scheme, and on the right is the temperature dependent programming scheme. So as as we saw in the previous slide, that because of the temperature change in whatever direction, the crossing point of those IV characteristics move up or down. So if this isense level of the chip can be moved up or down so that it always coincides with the crossing points of those IV characteristic, let it be at low temperature or high temperature. If it can follow the temperature, and if it can follow, if the isense level can follow the crossing points of those IV characteristic, then we will always get a very tight VT distribution. So which we call the dynamic sensing at this new crossing points. And in this temperature dependent programming scheme, the way we describe it is the first we will characterize the cells, like which cells are high temperature coefficient and which cells are low temperature coefficient. And during programming, let it be at high temperature or a low temperature, during the first programming, these cells need to be placed intentionally at locations that will minimize the cross temperature effect. Like in this figure, when it was programmed at high temperature, the red cells are placed at the leftmost tail, and the blue cells are placed at the rightmost tail. So when we sense it at a low temperature, the red cells will undergo larger VT shift, and the blue cells undergo smaller VT shift. But because they are placed strategically, they will end up being in the same region in the distribution. So the resulting distribution at a different temperature will not be widened. The same in the similar way, this scheme can be applied to the reverse experiment, where we can program it at low temperature and sense it at high temperature, and strategically place the red or blue cells in the programming distribution. But both of this scheme, they require significant redesign of the algorithms and circuitry, and they may increase program time. In summary, in all the states of a memory page, we observe that the threshold voltage distribution becomes wider when we sense it at a different temperature, which is summarized by these two figures. So from both of our experiments, we see that if we sense the memory page at a different temperature, the resulting threshold voltage distribution is always wider than the programming threshold voltage distribution. Now, according to our hypothesis, very high and very low temperature coefficient memory cells, they cause this cross temperature distribution widening, and this characteristic of high and low temperature coefficient memory cells comes from their subthreshold swing factor, which is the M factor. And according to our countermeasure techniques, cross temperature effects can be reduced by temperature hour program and rate.